John Belcher and I have had, what, 2 decades of association?
That's about it, right?
Yeah. And John was doing some very interesting stuff as I retired and came to hang out at MIT. And he let me hang out with him. And it was a lot of fun introducing studio physics into MIT's way of teaching introductory physics. But that's not what he's going to talk to us about today, because John has a long and distinguished career working on the Voyager project, as well as other things that I probably don't know about. But the Voyager project is, I thought, something be of interest to this group. Is it the only probe we have that is in actual interstellar space?
Voyager 1 is in interstellar space as well.
Yeah, oh, okay. So, but the Voyagers are the only ones.
Right.
Got it.
Yes.
Right, right. And so John is going to talk to us a little bit about that, and maybe what the future holds for some of these things. John?
Great. Thank you. Let me just say a few introductory remarks before I go over to my slides. I graduated from high school in 1961. That was the year that the solar wind was discovered by Herb Bridge, who was my mentor at MIT. I went off to Caltech for graduate school eventually, and worked on data for Mariner 5, which is a spacecraft that he had an instrument on. And then I came back to MIT in 1971 as a postdoc. When I came back to MIT, we wrote the proposal for Voyager and got it based on my mentor's reputation. He was very well known in the field. And then I spent, well, I'm still working. Yesterday morning, I was looking at data from the spacecraft. It was launched in 1977, so it's been sending back data from 45 years. When I say Voyager, I mean Voyager 2. Our instrument on Voyager 1 is dead. So I was just going to tell you a little bit about my experience in doing Voyager for the last 45 years. It's been fascinating to be involved with, and I'm very lucky to professionally have had that opportunity. This is the Voyager spacecraft. It was launched in 1977. The main antenna, that dish, is about 10 feet across. The RTGs to the left of the screen. This is the power source. It's a plutonium power source. We're in the process of shutting the spacecraft down. We have about another 2 years of life. It's nothing to do with the plutonium and the power source. It has to do with the fact that the thermoelectric effect that turns heat into power is getting less and less efficient as time goes on. So we're slowly losing power, and we're now getting to the point where we're having to turn off instruments so that we can still maintain communications with the ground. And we'll be doing that over the next 2 or 3, 4 years until we will only have one instrument running, which will be the magnetometer, which measures the magnetic field. And that's considered to be a really primary part of the mission. I'll explain as we go on, we're now out of the magnetic field of the sun. We're in the local interstellar medium, which has its own magnetic field generated by a totally different mechanism. And we're watching the interstellar magnetic field now and its interaction with the sun. Let me just point out how old the spacecraft is. The computers have plated wire memory. If you remember those days, this was something that came in after core memory. So it's a wire with magnetic plates on it. So it's really primitive memory. 3 main computers, each with a backup. So we have 6 computers. Each computer has 2,032-bit words. So we have really limited space in terms of running the spacecraft. Let me point out too that all these encounters going by Jupiter, Saturn, Uranus, they're all way, way far away in terms of light speed. So you don't do any of these encounters in real time. They're all done with computer backups that are loaded to the spacecraft before we go past the planet. and then the backup runs and performs all the measurements we want to make. But it's a totally automated process. And we can also change the way data is taken from our instrument and from the spacecraft in general. There have been a lot of adjustments in 45 years of the various data taking modes. So here's what I'm going to talk about. I'm going to talk a little bit about the concept of winds and cavities they blow out in the local interstellar medium. I'll give you some history of the Voyager mission. In particular, I'm going to talk about Voyager 2 crossing the termination shock in 2007, and I'll tell you what a termination shock is, and Voyager 2 crossing into the interstellar medium in 2018. So stars with stellar winds are common, and I'm looking here at a photograph of a star which is about 400 light years away. It's got a wind around it, which is blowing out at 400 kilometers a second from the star. And there is a bow wave as this star moves through the local interstellar medium. This is the local interstellar medium. Here's the star. There's a wind surrounding the star, moving at about 400 kilometers a second. That pushes back the local interstellar medium and causes a bow shock in front of it. So this is a shock, the shocked interstellar medium. And that's a very common phenomena in astrophysics. You see these all over the place. The one around the sun is very much smaller. This is light years across, and the one around the sun is light days across. But nonetheless, it's the same phenomena. So as far as the sun goes, Eugene Parker in the 50s predicted that a solar wind would blow from the sun. That was controversial at the time. It blows a bubble in the local interstellar medium. The distance to the boundary is set by the balance between ram pressure of the solar wind, rho v squared, which decreases as inverse r squared. V is more or less constant as you get away from the sun. And that pressure balanced against the interstellar thermal and magnetic field pressure. Once those are in balance, the solar wind can no longer push back the interstellar medium. It shocks up, and you have a very complicated interaction. Well, not that complicated. I'll talk about it. So that was Eugene Parker. In 1955, Leverett Davis at Caltech advanced the idea of there being a heliosphere using the arguments I just gave, and predicted it would be at 200 AU. And that was 6 years before the solar wind plasma energy spectra was directly measured in 1961 by Herb Bridge. And as I pointed out before, in 1961, I had just graduated from high school. I ended up at Caltech, and indeed Leverett Davis was my thesis advisor. So I have a historical connection to the whole field in terms of personal interactions with the people in it. Let me just say a little bit about the interstellar medium. As I say, the sun blows a bubble out into local interstellar medium. The local interstellar medium has two parts to it. There's a very hot part called the local bubble, which is very rarefied, 0.0005 per cubic centimeter and 1,000,000 degrees. But the interstellar medium is not a homogeneous medium. Inside the interstellar medium, there are different regions, and we happen to be in the local fluff. It's only a few light years across. The local bubble is thousands of light years across. What we're sitting in is the local fluff. It's much cooler, much higher density, and the sun at present sits in this warm, partially ionized medium. The local fluff is moving through that at a speed of 25 kilometers a second, and it will exit the local fluff in about 10,000 years to return to the very hot material that's 1,000,000 degrees. So the local fluff, and I'll be showing you some measurements of that, is relatively cool at 6,000 degrees Kelvin. It's partially ionized, and it has a density of about 0.2 per cubic centimeter, and it's moving with respect to the sun about 26 kilometers a second. So we've been in the interstellar medium since 2018, making measurements, and I'll tell you a little bit about what we see when we're in the interstellar medium. Let me just pause and ask if there are questions.
Well, one question is, does the fluff affect the amount of insulation on the Earth?
The fluff is pushed way back away from the Earth. All of this stuff gets blown back beyond 200 AU.
I see.
The fluff is a few light years across, but it's all blown back, and we haven't gotten into the fluff until we crossed the heliopause. That's the separation between the solar wind and the interstellar medium.
I see.
So when we crossed the heliopause in 2018, that's when we could see the local fluff. But we know a lot about it. All these things I'm describing are from remote measurements. If you watch light go through the interstellar medium, you see all sorts of things that the interstellar medium does to the light. And by looking at the light, we can deduce all sorts of things about the local conditions. For example, the local fluff is neutral. They're neutral hydrogen. I mean, it's not neutral, it's partially ionized, but the part that's neutral actually just drifts in to the sun, to the orbit of the Earth, and you can detect it in backscattered Lyman alpha. And you can decide, you can figure out what direction it's coming from and how hot it is. So that's how we get this 6,500 degree Kelvin, by looking at neutrals floating into the solar system, looking at the ultraviolet backscatter at Lyman alpha, and then we get some measurements about what exactly the neutrals are. So there's a lot of indirect measurements that gives us all of the local bubble actually emits X-rays. It's 1,000,000 degrees, so you can see the X-rays it emits. So all of these things are from remote measurements. I'm going to also tell you about a direct measurement of the local fluff, which is what we did when we crossed into the interstellar medium.
Go ahead. Ted, go ahead.
Yeah, so what about the effect of the local fluff on the flux of galactic cosmic rays?
I think the flux of galactic cosmic rays is pretty much independent of the local fluff. I'll be showing you some measurements there. I think the galactic cosmic rays is so energetic that they don't pay much attention to the local fluff.
Yeah, high density of neutral hydrogen, you'd be scattering some number of those protons.
The bigger effect, as far as we're concerned, on the cosmic rays is that they get pushed out of the solar system just like the interstellar medium does. So we've never been looking at the true cosmic ray spectrum, because the low energy cosmic rays can't get into the Earth, or at least they get into the Earth very diluted because of all this complicated interaction. And of course, cosmic rays are ionized. So there's a huge effect on the cosmic rays from just the fact that the solar wind exists, not so much the local fluff doing things to them.
Well, what about charge exchange? So you get high energy neutrals?
Yeah, when we do see that, we see charge. There are Earth orbiting spacecraft which can measure high energy neutrals, and they see the high energy neutrals that come from charge exchange with low energy stuff, then getting neutralized, and then you can see that at the Earth. So yeah, no, that is a significant process, and it has observable effects.
Let's let you go on now.
Okay. So let me just give you some dates. Voyager 1 crossed the termination shock in December 24. I'll say something about, I'm just going to give you some dates and then move on to some graphics. So the Voyager instrument on Voyager, the plasma instrument on Voyager 1 has been dead since 1981, but we've been fine on Voyager 2. Voyager 2 crossed the termination shock in August of 2007. Then Voyager 1, which is ahead of Voyager 2. Voyager 1 is maybe 20 AU ahead of Voyager 2, and AU is the distance from the sun to the Earth. These spacecraft are about 100 AU away, and Voyager 1 is 20 AU in front of Voyager 2. So Voyager 1 was the first to cross into the interstellar medium, and finally Voyager 2 crossed into the interstellar medium in 2018. And I then decided to retire because we made the first direct measurements of the interstellar plasma. So let me just get those terms a little more solidified. This is the region where the solar wind is coming out very fast, hundreds of kilometers a second. It's blowing back the interstellar medium. This is the interstellar medium. Eventually, it can't blow it back any further because its ram pressure is going down as it goes out. Then it has to shock up. So previously, it's supersonic and 400 kilometers a second, maybe Mach 10. Then it can't go for push the interstellar medium back, and it shocks up. That's the termination shock. So that's what I was talking about, crossing the termination shock. Inside here, we just have the supersonic solar wind. Then we cross the termination shock. The speed goes way down and it gets really hot. And then it starts to turn and move back down the tail. And this is the direction from which the interstellar medium is coming. And it just happens fortuitously that both Voyagers are going out into the interstellar medium toward the nose. That's a total accident. We didn't plan that. So that both of them have gotten to the interstellar medium. If we had gone the opposite direction, we would probably never have gotten to the interstellar medium. This is the shocked solar wind leaving a trail behind the sun in the interstellar medium. So are there any questions about the geometry?
I have a question.
Yes.
So what we have is the yellow spot is the sun. The lines around it are the various planets, and the sun is putting out a solar medium that is reducing in speed as it gets further away from the sun.
Actually, it's very strange. It's moving at constant velocity when you get away from the sun, but then it's reducing in density to keep rho v squared. I mean, to keep rho v r squared constant. The flux constant.
Then it undergoes a significant change when it hits the termination shock area.
Right. It becomes very cool. Yep.
And then it's acting a little bit like a comet because the whole solar system is moving from left to right here.
The whole solar system, well, I'll use the word heliopause occasionally. The heliopause is the separation between the solar material and the interstellar medium. I think the question before we got bollocksed up was the sun is moving. This is, well, you can either say the sun is moving or the interstellar medium is moving. The sun is moving to the right, or if you go to the rest frame of the sun, the interstellar medium is moving to the left. In any case, the interaction between them is the direction that the sun is moving into the interstellar medium. As I said, it's an accident that we happen to be going out the solar system in that direction. The way we're going out is totally determined by the orientation of the planet so that we could do the grand tour. Remember, energetically, the reason we could do Voyager was we went past Jupiter. We picked up a little gravitational assist from Jupiter, which got us onto Saturn. Again, we got energy from Saturn to go to Uranus and then on to Neptune. So each planet we were picking up energy, and which direction we went out was totally determined by which side of the planet all those, each side of the sun, all those planets were on. So we happened to be going out into the actual interstellar medium. So that's fortuitous and one of the many lucky things about this mission. So I'm going to switch over and start talking about some of the data from our instruments. As I say, we're dead on Voyager 1 for a long time. Voyager 2, we've been getting data since launch. What we have is a modulated grid Faraday cup. So this is, we have 4 detectors. All the detectors are open to space, but we have a grid through the window. We have a collector in back of the grid, which measures current that falls on it. And we modulate the grid with respect to the collector from 10 volts up to 6 kilovolts in small steps. And as we do that, we exclude more and more, for example, the protons, so that we can get a measure of the distribution function of the protons as we step from 10 volts to 6,000 kilovolts. So this is the main sensor. This looks back toward the sun. And this is the side sensor. This is where we make measurements at the planets. And also this is where we've made measurements of the interstellar medium. Okay, so let me show you from the data, some of the data. This is the a typical measurement. It takes us like a minute to do this. We step from 10 volts here to 6 kilovolts here. And we're going back and forth very rapidly, and say from 50 volts to 60 volts and back to 50 volts and back to 60 volts. We synchronously detect the change, and that gives us a measure of how many ions, positive ions, for example, there are between 50 volts and 60 volts, because we're measuring the change in that. So as we move up, we see very little in low energies. When we get to about 400 volts, I'm sorry, about 400 kilometers a second, which is about a kilovolt, we see a peak. And we also see a spread about the peak. The spread about the peak is due to the thermal, the temperature of the plasma. The fact that the peak is way bigger than the spread just means that this is highly supersonic. As I say, the peak here at 400 volts compared to a thermal width of maybe 40 or 50 volts means that this is Mach 10. So this is the supersonic solar wind blowing out from the sun. This is at 30 AU. And that's what we were measuring up until 2007 when we crossed the termination shock. Okay, so let me show you some of the results from our measurements before we got to the termination shock. This is launch in 1977, and this goes through the termination shock, which was in 2007, so a little bit into the Helios sheath. The Helios sheath is the shock solar wind. And when we come to the end of the Helios sheath, we cross the heliopause into the interstellar medium. So here's the density we were falling off roughly as 1 over r squared as we go out. Note we start off with a huge density of 10 per cc at 1 AU. So this is a very tenuous plasma. It's by anybody's standards a high vacuum. It's not very dense. I'm going to show you the speed next on the same time scale. So here's launch. The speed of the solar wind is typically 400 kilometers a second. You see lots of structure here due to the solar cycle and to various sources on the sun as they rotate under the sun rotates every 30 days. If you do a spectral analysis of this, you'll see a big peak at 30 days. A lot of this is solar rotation. So we, for years and years and years, 1977 up to 2007, we saw this very high speed. And then all of a sudden the speed goes way down. That's because it's shocked up. So it's going very fast and it's very cold, and then it shocks up, it gets very slow, and all of that energy goes into heating it up. So
What does shock up mean?
shock up means if you think of the bow shock in front of a jet, the jet is coming through the air initially in front of the jet is sitting there, doesn't see anything. The jet is moving supersonically, and because it's moving supersonically, information that it's coming cannot get ahead of the jet and tell the air to make a smooth transition to the fact that the jet is coming. So when I say shock up, it means that because it's moving supersonically, you get a barrier where all of a sudden the information gets to the wind that it has to move, and then it starts trying to move with the jet, and you get a sonic boom, and that's the shock in front of a jet plane. So here the solar wind is going out at very high speeds. It's pushing back the interstellar medium until finally it can no longer do that. Because it's moving supersonically, you don't have a gradual transition. You have to have a very thin transition, so that it shocks up. I'm not sure I'm explaining the physics right, but basically you're moving so fast that the material you're moving into can't get out of the way. It doesn't know you're coming. And the way you affect the transition is you have a very rapid decrease in speed and an increase in density and temperature. So that's the speed. Next, I'm going to show you the temperature. And now I've switched over to degrees Kelvin. It starts out very hot and then it cools down. It doesn't cool down a lot. I won't tell you why that's so constant. But then when we get to the termination shock, it gets very hot and it goes back up to close to 1,000,000 degrees Kelvin. That's because the speed has gone down and all that kinetic energy and the streaming motion has gone into random motion. Okay, I'm actually, this is long-term averages. I'm actually going to show you the structure when we cross the shock. This was one of the big highlights of the mission, to actually get out of the influence of the solar wind. I'm not going to tell you a lot about this, but I just want to show up on top is speed. We actually crossed into the shock solar wind in a data gap. So we didn't actually get the first crossing. But then the solar wind got more robust and it expanded out the distance to the termination shock, and we went back into the supersonic solar wind because that boundary, the shock is moving out. So here we're very high velocity wind. We're coming from low velocity wind. This is shock material. This is not shock material. And then the heliosphere expanded again. Shrunk again. So we went back into the shock solar wind. So we crossed the shock. So this was very fortuitous. We got many shock crossings. A lot of the interesting things that the physics was what was the nature of the shock. This is a collisionless plasma. It's very dilute. And there's a lot of theory about collisionless shocks and plasmas, and we verified that a lot of the theoretical models are okay, because we measured the thickness of the shock, and it's about what you expect based on plasma kinetic models of collisionless shocks. So I'm not going to say a lot more about that. Okay, so we got to the.
I had a question about the data. I don't know if now is a good time. I don't want to interrupt the flow, but I'm kind of curious about. So you can put this off if you want, but I'm curious about how much data this is, and how you compress it and communicate it. I mean, it sounds like this is just one point, but it's multiple dimensions. that you're measuring as the spacecraft is moving, but is like what kind of sample rate and how do you compress and transmit this over these kinds of distances with the energy you have on the spacecraft?
The big data rate driver in the spacecraft, of course, is the pictures, but the cameras have been turned off ever since we went past Neptune. We only have a data rate of about 200 bits per second. It takes us maybe 3 minutes to make a measurement. So when this is a 243, this is a transition from day 243 to day 244. And you can see that the measurements are roughly 3 minutes apart. So that comes down to the spacecraft it comes down to the Earth in bits, and we get that and have all sorts of computer programs that pick apart the data stream and reconstruct the plasma distribution and analyze it. Incidentally, we have no problem communicating with the spacecraft as far as it out. We could probably communicate with the spacecraft for 10 times further out. That's surprising because it's a 30-watt transmitter, but we're using a deep space net to pick it up. So it's not the communication that's causing us to shut off the spacecraft, it's the power degradation.
I seem to recall an article I read years ago that the protocols you're using have been upgraded several times in the course of the mission to improve compression and transmission. But the hardware, it blows me away that you're able to stream all this. I mean, you don't have memory to keep it. You have to stream it as you're getting it, right?
Right. We do have a tape recorder on board, which allows us to take data faster and then play it back slower. But we don't use that at all, and it's very rarely used. So it comes back directly. Yeah, that's why when I said we were in a data gap when we crossed the shock the first time, we were not receiving data on the ground at that time because of the location of the deep space net. And then luckily we came back and started tracking it again and got the actual shock crossing, or at least 2.5 of them. So that was really fortuitous, but it's because we're streaming the data. It doesn't go into tape recorder. Once it's streamed, we can't get it back. Okay, so here we are. We were launched in 77. I just showed you we are going through the termination shock in 2007. So we saw that transition to the supersonic to subsonic flow. We also saw the flow. So now we're in the heliosheath. The heliosheath is the shock solar wind. When we come to the heliopause, we'll actually go into the interstellar medium. But when we cross the termination shock, we're not anywhere near the interstellar medium. We're just looking at the shock solar wind. So this heliosheath, the sheath around, and that's hot solar material. So we're looking still at solar material in the heliosheath. So that was in 2007. The big question was, were we going to get out into the interstellar medium? And Voyager 1 did it first, but our instrument was dead on Voyager 1. So we didn't take part in any of that excitement. But Voyager 2 was still going. Let me show you some data from Voyager 2. Here's the shock back in 2007. Then we were in the heliosheath. This is speed vertically, so it's low speed. No, it's not terribly low speed, but anyways, this is the heliosheath. This is hot solar wind, and this goes about to 2015. So for 11 years after the termination shock, but before crossing into interstellar space, we were in the heliosheath. And we could make measurements fine. We got a lot of interesting science out of measuring the flow, turning and going back and down the tail. The real question was, would we see anything in interstellar space when we crossed? The speed and thermal speed of the plasma, interstellar plasma, is about 220 kilometers a second. And our instrument was never designed to measure. Our lowest energy channel starts at 44 kilometers a second. So we're looking at plasma that has got energies way below our lowest energy channel. And moreover, we're looking in the wrong direction. Our side looking cup is sort of the closest to the interstellar flow direction. The main sensor is looking opposite the interstellar flow direction. So we weren't sure that we would see anything, just we weren't looking at the right direction. We weren't looking in the right direction, and also the plasma we were moving into is not very energetic. It's below our lowest energy channel. So we're waiting. Finally, in 2018, we crossed from the heliopause into the interstellar medium. I'm showing you data from the cosmic ray experiment. So these are galactic cosmic rays. When I'm inside the heliosphere, galactic rays have a hard time getting into that. So we see galactic cosmic rays intensities go up when we actually get into the interstellar medium. So that's the sure sign that you crossed a boundary into the interstellar medium. There's also a lot of low energy particles, solar energetic ions. These are less than 0.5 MeV per nucleon that are generated inside the heliosphere. And when we get outside of the heliosphere, they go down to zero because you're outside of the region where they're being generated. So this is really a clear indication on Voyager 1 that we had gone through the heliopause. So what did we see? So we know the timing. We know the timing when this is coming along. Here's instrument data from our instrument. These are the currents in the main sensor, main sensors. And as we came into that transition, when the cosmic rays told us that we had crossed into the interstellar medium, we saw our currents in the main sensor go to noise. But we still have data from the side sensor, and that didn't go to noise. This is the one that's looking closest to the direction from which the interstellar medium is coming. These sensors are looking almost 180 degrees away from the direction that it's coming. The interstellar medium is coming. And what we saw in the side sensor, in the main sensor, the plasma disappeared. We saw significant currents only in the side looking cup. In the lowest channel, which goes from 10 volts to 30 volts. And the current in this channel gives us a lot of information. We actually see the interstellar medium. I'll tell you why we think we're sure we're seeing the interstellar medium, even though it's very low energy and way below what we were designed to measure. Here's how we know that we're seeing the interstellar medium. Because we can do rolls on the spacecraft. This is the direction to Earth. And this is the normal orientation of the spacecraft. Here's the wind direction. Here's our sensor. The wind direction is sort of coming about 60 degrees away from the normal to this side looking sensor. It has a 60-degree field of view. So the interstellar medium is just coming into at the edges of its field of view, and also it's coming in at low energy, so we can only see the signals in the lowest energy channel. So if we were stuck in this situation, we would really not know much about the interstellar medium from our measurements, but we can rotate, we do a roll, you can rotate, the spacecraft is 3-axis stabilized. That means it's continually pointing the sensor at the Earth. We have to have that to be able to communicate because we're so far away. but we can also roll about that direction to the Earth without losing communication with the Earth. And we do that periodically to calibrate the magnetometer. And we also do it now so that we can see the properties in the stellar plasma. So when we do a roll, we're rolling about this axis. It takes the side looking sensors normal. It rotates it all around. It will come back and point directly into the direction of the interstellar flow and then come back to where it was. And because this is a transonic plasma, it's moving about as fast as its thermal speed. We will get a really pronounced anisotropy depending on whether we're looking totally away from the flow or directly into the flow, because the flow is transonic. So this is what we see. And this is why I believe we're measuring the interstellar medium. This is a roll that we did. They don't take long, about 80 minutes. Here's the current in our side-looking sensor, the lowest channel. So here we're looking not too far away from the interstellar direction. And so we see some data. When we go into the roll, what we're doing is sweeping our side-looking sensor away from the direction of the interstellar medium coming in. And eventually we get almost 180 degrees opposite that direction. And we see a real pronounced minimum. That's because we're sitting in a transonic flow and we're looking opposite the direction of the flow. So we're not getting everything because it's transonic. When we continue on with the roll, when we're looking in the direction directly into the interstellar flow, we see a peak. Okay, so you can imagine that by studying the shape of this curve, we can determine a lot about the plasma that we're in. First of all, we can get the direction of it. And by looking at the width of this decrease, we can get a measure of the thermal speed. So by looking at the shape of this, when we're in a roll, we can get good estimates of the plasma properties of the ionized component of the local fluff. And the forward backward asymmetry is a measure of the Mach number of the flow. Again, it's about Mach 1, but it's enough to give us a lot of information about the thermal speed. I stop for questions.
Yeah, on the data that you're showing, it looks as though, at least to me, it looks as though you have some oscillation around the trend that you're showing. Is
Yes.
that real?
We're very close to, this is in femtoamps. We're very close to our noise level. I'm not sure that's real. It could well be real. It's just the overall, the thing that we're really excited about is seeing the overall shape.
Yeah.
So I have a question. When did you realize this neat trick would work? Like, how far away was the spacecraft when you decided you could do this with the roll?
After we went into the interstellar medium and we could see that what we never anticipated using the roll to actually see if we were there. It's funny, we should have thought about it, but
it's fascinating.
Yeah, no, we crossed into the interstellar medium. We weren't seeing anything except in the first channel. Of course, you're only making one measurement and you're trying to figure out what the density, the thermal speed, and the velocity is. I mean, so we sort of knew it was about right, but then we had a roll coming up and somebody said, hey, we should look at a roll. But that was the first time we really thought how important that would be for characterizing the data. So I
read about the roll with the cameras to take pictures of on the flybys.
Right.
The shutter speed was so low that they had to pan the camera, and they used this roll with low light and high speeds to sharpen the image. But this is just fabulous. And they didn't understand that. I don't think they planned on doing that either. It was
They
an
did not.
invention
Yeah, that was
in the middle of the flight.
Yeah, that was all when they realized we were actually gonna get to Uranus and Neptune.
Mind blowing.
Remember that? Yeah, no, it's mind blowing. The lifetime of the spacecraft was 4 years. So we expected to get to Saturn and Jupiter. After that, it was just all luck. But here we are 45 years later, and the spacecraft are both working. It's absolutely amazing.
I think it's good engineering too. I mean, it's amazing that you have the discipline to be able to invent and squeeze new functionality out of something that you can't touch. That's good engineering too. And not
Yes,
just
no, it's wonderful engineering. I would also say that it's wonderful management. The fact to have an organization that runs the spacecraft, they are continually putting up computer loads, they're continually communicating with it. To actually have that all organized so that you don't lose the spacecraft, and it would be very easy to lose the spacecraft. It's just remarkable that that's gone on for 45 years. The engineering was fantastic and the management was fantastic.
John,
Steve,
can you comment on the variability of the or diversity of the quality of the scatter of the data in some of those plots? Some of the plots show a huge amount of scatter in the data. If you go back maybe 3 slides or so, 4 slides to where you're talking about the data over long periods of time. Maybe one more back. Yeah. No, more than that. Okay. Yeah. So if you look at that density plot, for instance.
Right.
The density plot, there's a huge amount of scatter.
Right.
On the speed plot, there's less scatter. And then on the temperature plot, the scatter varies over the course of time, more pronounced than in any of the other ones. Is there anything that's going on there that we're not really understanding?
Well, most of the scatter is because of, as I say, the sun rotates every 30 days. And if you look at the solar surface, there are regions where the magnetic field is open and where it's closed. So there's some regions which are putting out a lot of solar wind. And then, so if you're sitting right above that, you'll see a lot of solar wind. The sun will then rotate so that you're over a magnetic field structure that's closed and not a lot of solar wind is getting out. So that modulates what you see at 1 AU with a period of about 30 days. So when I see all these spikes here, that's almost certainly solar cycle variation. I'm not solar cycle, solar rotation. It's a 30-day period. And that's what's driving all that. It's pronounced in the density. It's not so pronounced in the speed. Let me just say something about the thermal speed. This actually, if there were no, well, there are 2 things that keep the temperature up. There are lots of streams colliding as you have low speed and high speed. But the other thing that keeps the temperature up is the interstellar neutrals drift into say 10 AU, they get ionized and they get picked up by the solar wind. And that heats the solar wind. That pickup process heats the solar wind. So some of this heating here is the fact that we're already interacting with the interstellar neutrals way before we get to the actual interstellar medium, because the interstellar neutrals can just drift across all this barrier and get into the inner solar system.
Mike has his hand up.
No, try it again.
Oh. Then when you see the speed data, you see a lot of scatter early on, and then it becomes cleaner in a sense as you get out further. Is that the same phenomenon going on in reverse?
Yeah, it's a lot of variations early on, but these streams are moving at different speeds and they collide. So when you get further out here, they've had longer to equilibrate. So the speed difference goes down because the speed difference along a radial line causes them to continually bump into each other. And that will tend to equilibrate to a common speed. So all of this stuff was before there was a lot of, this was about 1985 was Uranus. So this is, that's right. So this is about 20 AU. So this is the first 20 AU. It settled down because it's interacting as time goes on.
Mike has a question, and I'd also like to. Mike has a question. I'd like to know if we can get him in. Also to note that we're only have 30 minutes left, and I'm not sure how far along John is. Can you hold off a second and let Mike ask his question?
Sure. Yes.
Okay, I just wanted to know. Wait, yeah, yeah. You're. How much of fuel do you have to be able to drive the reorientation of the spacecraft?
We have essentially an infinite amount of fuel. We use hydrazine jets, and they totally pack the spacecraft with more hydrazine than they would ever want to use, because they were anticipating that we would get out. When we were talking earlier about this way to take pictures at Neptune and Uranus, where you slew as you're going past so you don't get blur, that's all done with the hydrazine jets, and that's a 3-axis motion. It's not just rolling about the Earth, sun, the spacecraft sunline. It's orienting all axes of the spacecraft. Early on, Voyager was called the Grand Tour. Well, what the Grand Tour evolved in was Voyager. The Grand Tour was an extremely expensive mission that was going to fly the same trajectory as Voyager, but it was going to build a spacecraft so you could reliably predict that it would last for 30 years. And that means a huge amount of redundancy and a huge expense. So the Grand Tour got canceled. What replaced it was Voyager, and it just had a 4-year lifetime. So you weren't putting all that money into redundancy and making it last for 30 years. However, we always wanted to keep going, hoping that things would work out. And a crucial thing is the hydrazine, because you need that hydrazine to do all these fancy things at the planets with the camera. So the engineers, even though they had a mission that only had a 4-year lifetime, they not put enough hydrazine on board to last for 45 years because they hoped that this would happen. So there's no problem with hydrazine, that we could spin the thing around and make it dance up and down. We have plenty of hydrazine to maneuver it. Actually, one of the problems we have is we're shutting off instruments, and the instruments provide a local heat source, and some of the hydrazine lines run close to the instruments. And one of our worries has been we would shut off an instrument and thereby freeze up that hydrazine line. And then we would no longer be able to maneuver to point the antenna at the Earth. So that was one of the failure modes that we've been worrying about for the last couple of years. But so far we've been turning off instruments and we haven't had any effect on the hydrazine being frozen up.
I mean, isn't that a motive for not turning off instruments, even if they're not working?
It is a motive, but we can see a slow decline in the efficiency of the thermoelectric process. So we have 300 watts to run the spacecraft, and it's slowly declining, a very predictable thing. So at some point, like our instrument takes 9 watts. At some point, they'll turn us off to get that 9 watts back so they can use that to communicate with the Earth. And they will have to turn us off if they still want to communicate with the Earth and run the spacecraft. So you don't want to do it, but on the other hand, you have no choice. You have to get power from somewhere to run the spacecraft.
But what's the point of running the spacecraft if you can't make any measurements?
You want to run the spacecraft until there's one last instrument running. And that instrument will be the magnetometer, because, well, maybe one of the cosmic ray experiments, but the magnetometer, I think, is the most important thing. It's measuring the interstellar magnetic field and how that, well, I think it's important to measure the magnetic field. So yes, there's no point in running a spacecraft if you have no instruments, but you've got to cut them off one by one so you can still run the spacecraft for the sake of that last instrument.
It's kind of the lifeboat problem, you know. You have to start eating each other until there's only one left.
That's right. That's right. And it may be that we're 45 years now. It may be that they will eke out enough power to last for 50 years. But sometime, I think in the next 5 years, there won't be enough power to run the spacecraft and we'll not be able to communicate with it. Okay, so just to remind you where we're going, this spacecraft never comes back to the Earth. It's moving away from the sun. It will cover 4 light years in roughly 30,000 years. So we're moving toward Alpha Centauri, sort of. But of course, we're going to be dead in 5 years, so it doesn't make any difference whether the spacecraft gets to the stars or not. But still, it's a really amazing concept to think that we have put something out in space away from the solar system, well away from the sun, going basically in interstellar space. And this spacecraft basically doesn't decay. That is, it's sitting in a very dilute energetic particle environment that causes some weathering, but the weathering is minuscule in the sense of it takes 1 billion years to do a significant amount of weathering. You know that there's a golden plate on there, which has a lot of information here and a lot of recorded photographs and a lot of instructions as to how to read the plate. Of course, the chances of that ever being found by anybody or zilch, but nonetheless, it's interesting to think that this will be out in space long past the demise of the Earth. The Earth will, the sun is currently burning hydrogen. It's been burning hydrogen for 4 billion years. Eventually, it's burning that into helium. Eventually, it will run out of hydrogen, start burning helium. When that happens, it goes into a red giant phase. The atmosphere of the sun expands out to the orbit of the Earth. The Earth then cycles in and is burnt up by the sun. We could possibly go to the moons of Jupiter if we want to survive as a species, but because that won't be enveloped by the red giant atmosphere, but the Earth will cease to exist. But this will still be out there, which is quite amazing in a philosophical way. Let me also say that the chief engineer on our instrument who built this amazing experiment, a guy named Bob Butler, he was from New Hampshire. And on one of our collector plates, I told you that we have metallic collector plates behind the grids that collect current. He wrote on the top of the collector plate, live free or die. That's the New Hampshire state motto. And then he wrote the names of everybody who had been associated with building the instrument on the plate. And right down at the bottom is my name, because I was a real peon in those days and I didn't have much to do with building the instrument, but nonetheless, my name is there. The amazing thing about that is my name will be there a billion years from now. So you're talking to somebody who literally is going to live forever in some sense. I just think that's fascinating. It's personally egotistical to think about that, but it just gives you an idea of the scope of all this and the scale of what Voyager has done.
Well, and of course, now we know somebody like that.
That's right.
Thank you, John.
Right. So let me just finish with mentioning Herb Bridge. He was my mentor at MIT. He's the one who brought me as a postdoc. He helped me get through the tenure process at MIT, which is Byzantine, I think is probably a good description of it. And he's the one who's basically built this instrument, hired the engineers who built it, and made it a success. Also, here's a picture of me in my younger years. I was 34 when the spacecraft is launched. I'm now 79. So it's been most of my professional scientific career looking at data from this thing. And it's been an amazing thing to be involved with. So that's about what I wanted to say.
What is Voyager 1 doing now? Nothing?
Voyager 1 is in the interstellar medium going in a very different direction. We are dead on Voyager 1, but all of the other instruments on Voyager 1 are working. So it's going out north of the equatorial plane, the ecliptic plane, the plane of the planets, and Voyager 2 is going out south. But it's still working fine, except the plasma instrument on board is not working.
Oh, is it? Okay.
So when I tell you about all this, I'm talking about Voyager 2 data. Our Voyager 1 instrument died in 1981, a few months after Saturn encounter. So it really hit the design lifetime of the instrument.
But there are other researchers who are quite happy that Voyager 1's still there.
Oh yeah, no, there's a whole, yes, there are 2 cosmic ray experiments, a magnetometer experiment, a plasma wave system that measures electrical noise, which is very useful in determining the plasma density, absolutely, because we see oscillations at the plasma frequency, which depends on the density. So by observing those oscillations, you get a good measurement of the density. No, there's a whole set of people doing observations with Voyager 1 and Voyager 2, watching to see what's happening outside in the interstellar medium, for example, over the solar cycle. The solar cycle has a huge effect on cosmic rays because they have a hard time getting in to this very turbulent medium. So Voyager 1 gets to sit outside and watch all this and compare that to Earth-based satellites who are watching the cosmic rays being modulated by the solar wind. So there's a lot of research, ongoing research to do with data from both spacecraft.
You realize you're making a 4-year satellite into a 40-year satellite. Makes it really hard for your successors when they put proposals to say how long will they have to last.
Well, I tell you, it also makes it very, very hard on the personnel because I'm the I was the second PI. Herb Bridge stepped down. I became the principal investigator. I stepped down, and John Richardson at MIT became the principal investigator, who I always think of as a young man, but he's but he's 69 years old.
Are there plans for any further instrumentation or devices to be sent out?
There's a plan to, China's very interested in sending a mission to the interstellar medium. So they really have very active plans to do that. The reason they want to do that is because everything on this plate is in English, and they would prefer to have a plate in Chinese.
Now, is it true that one of the images that's encoded on the plate, right, is part of this, I don't know however many images that they put on the thing, right? And one of those images is a view of downtown Boston, essentially taken from MIT.
I don't know that specifically. I would imagine that that's true. There are only 400 images. It's a very small number, and some audio recordings. But I think
there's a view. You can see that many of the buildings are hidden by other buildings now. But if you know which way to look, you can still see some of the buildings that are, if you try to figure out where that picture was taken, it's essentially got to be somewhere along the Cambridge river bank there, and my guess is it's somewhere right around MIT.
Yeah, no, I didn't know that. That's interesting.
Yeah.
Although I tell you, one of the most interesting things about this plate is Carl Sagan said, it's never going to be found by aliens because the probabilities are so low. It's much more probable that we will go out and get it because we know exactly where it is. And depending on
Mike, you have a question?
Yeah. I've been puzzled by you're using the term interstellar magnetic field. At least locally, magnetic fields have a direction. And can you sort of expand on what you're measuring when you measure the interstellar magnetic field?
The direction and the magnitude. So they're measuring a vector, and the Earth's magnetic field is generated by turbulence in the core, a dynamo mechanism which pumps energy into the magnetic field. The sun's magnetic field is the same thing, turbulence in the center of the sun. The interstellar magnetic field is also dynamo generated by motions in the local arm of the galaxy, and it's got a very different orientation, but about the same magnitude as the solar magnetic field very far out.
So are you able to actually compare what you're seeing to calculations of the sort you were just describing?
Yes.
Wow.
Hey, John, are they able to correlate the data between Voyager 1 and Voyager 2 to learn anything from that set?
Certainly in the energetic particle experiments, yes, because they see a lot of differences in the Voyager 1, Voyager 2, the cosmic ray levels. So again, even though we're outside the region controlled by the sun, we still have a lot of things going on which are solar related. For example, there'll be a huge flare on the sun. It will make the heliosphere expand. So the boundaries of the heliosphere will expand. The termination shock will move out. And that piston driving into the interstellar medium will generate a shock in the interstellar medium, driven by the fact that the heliosphere is expanding. So when you get out and you're looking at Voyager data, you will see that shock in the interstellar medium go past Voyager. But that's a shock in the interstellar medium, but the energy source ultimately came from the the sun, because it's making the heliosphere breathe, and that generates disturbances in the interstellar medium.
And can I ask an ignorant question, please? Is that analogous to a gravitational wave as we're learning about?
Gravitational wave in what sense?
I don't know enough to ask it more precisely than that. That's my problem.
It's not gravitational, no. It's just fluids interacting.
Okay, fair enough.
So one question, John, that has to do with art. You show an artist's conception of the local area of the heliopause and the shock and things like that. I've seen one where there's two tails on the downstream side. Is that just an artist's idea, or is there some science behind that?
I've never seen one with two tails, although there's a lot of complicated ones out there. But so I can't speak to whether there's any science to that or not. I'm not aware of that particular.
Yeah, the image looks very similar in the sense of the artist's conception, obviously, but downstream in the heliosphere, it ends up having tails that are one on one side and one on the other side, and obviously it's a two-dimensional view of something that's obviously three-dimensional.
What you might be thinking about is the magnetic field of the sun is pretty much perpendicular to the ecliptic plane. So the sun has a magnetic field that comes out and interacts, and if people follow it theoretically by going down the tail, and the south, the magnetic field also comes out of the South Pole, and it interacts differently. If you showed illustrations of where the field is, it might show a double lobe structure because of the fact
that it could be. I don't remember precisely where I saw it. It was in somebody's paper, but it they said, well, this is kind of just to give us a sort of reference point of view, and I think it was the International Boundary Explorer data or something like that. It's the optical.
Yes. I'm not. I know what the. Yeah. I don't have anything else to add to that.
Great presentation. Thanks, Jeff.
It's a wonderful story, John. Both what you've learned and just the fact that it's lasted this long gives it a whole aura of achievement that's quite marvelous. I mean, really,
yes,
one marvels at it.
Yeah, one marvels at it. Yeah, and I frequently I teach a lot of E&M at MIT. I frequently tell my students that in the 1890s, Marconi could send a radio wave across his attic 30 feet. And it's now 2022, not that much time since the 1890s, and look what we're doing. So when I say things like, we may go out and get these spacecraft, that's the best possible future.
If we're around to do it. Yeah.
Yes. Yes. Yes.
All right. Oh, that's great.
I like the concept that the most likely interaction, if there is any interaction between intelligent life forms, the most likely one is to encounter a space junk. Right? We're going to find someone else's space junk, or they're going to find ours, because
right,
it's going to outlast us long after they were active, so they won't be functional. I just thought that was kind of interesting.
Yeah, well, of course, it's a great puzzle as to why we're not seeing a lot of radio traffic. If there are a lot of exoplanets is the exciting part of astrophysics now, and what they've discovered is just about for every planet, every sun, there's a planet. I mean, it's not a rare occurrence to have a planet, it's sort of unity occurrence. So if you think of all of the stars in the galaxy and you think of all the galaxies, there are a huge number of planets. And you would think that there would be life on other planets, and you might think that we should be detecting radio emissions from them, but we don't. So there really is a conundrum there.
Perhaps they shift over to neutrino communications very early in their technology. And so
unfortunately, I think the answer is global warming.
No,
or nuclear destruction.
Oh, nuclear destruction. That too. Yes, right.
If this junk is going to last 1 billion years, and how long is the radio signal that our society is producing could last hundreds or thousands of years, but the junk that we're putting out there will last billions of years. So the probability of encountering someone's junk is much higher than radio transmissions.
Isn't it really the probability of our junk encountering their junk that's high?
It could be that.
Right. The thing is that space is really vast. It's enormous distances, and that is I mean, I'm an astrophysicist. I've sat in an astrophysics division for 50 years, and it still does not come home to me how vast the universe is. I mean, it is really big.
Some of the stuff. I mean, what strikes me is the fact that you're looking at phenomena that our sun is producing that interacts with what's out in the cosmos. But other stars are doing the same thing.
Right.
Are you able to, with Voyager 2, are you able to pick up any kind of signals that would demonstrate what the other stars are doing, how this interaction is occurring?
No, because of the distances involved. As I say, from here to here took us 45 years. To get to the nearest star will take us 30,000 years. So the distance to the nearest star is just humongous. And that's only 5 light years.
Now we have also got 2 Pioneers and a New Horizons.
Yes, right.
And they're presumably going to end up doing, I guess Pioneers were slower, so they're even though they were launched earlier, they're way behind. Is that right?
That's right. And also the Pioneers went out the tail. Again, it's serendipitous. So they weren't moving toward the optimal direction.
What about New Horizons? Where is that going?
New Horizons will is looking at going in the right direction, but it's got to last for a long time to get out to the interstellar medium. But they're still
somewhat faster though than the Voyagers, right?
Yes, that is right. Yeah, they're moving at a good clip. That's right.
John, I'd like to thank you very much for speaking today.
Sure, it's a delight to do this. Thanks for asking me.